All right, good morning. We'll go ahead and start the webinar. My name is Hugo Zhou. I'm a professor from Auburn University. So today's webinar is sponsored by Stride Center. Stride is a 2016 USDOT Region 4 UTC. We are a consortium of 10 Southeastern college and university with the University of Florida as a lead institute. Our mission is to develop a novel strategy for reducing congestion. We would like to invite you contribute questions at any time through chat box, and we'll answer them at the end of the talk. So today's webinar is on the project evaluation of walk zone mobility by utilizing naturalistic driving study data phase 2. And I will present this with Dan Xu. Dan Xu is a Ph.D. student from Auburn University. So this is a content outline for our presentation. I will talk about the background and objective. Dan will present the methodology, results, and the conclusion and the potential application. So the background, this is a two-phase project funded by Region 4 UTC. The phase 1, the project started August 16, 2018 and end August 15, 2019. The final report has been published on the Stride website. You can click that link to download that report. This webinar is on the phase 2. And the timeline is from March 16, 2020 to November 30, 2021. So we are currently working on the final report. So any question and comments received from this webinar, hopefully we can still address in the final report. So some little outcome from this phase 2 project. We had the TRB paper entitled Analysis of Headway and Speed Based on Driver Characteristics and the Walk Zone Configurations using NDS data. That paper has been published recently in the 21st Journal of Transportation Research Board. It's already out there. You probably can download that paper. And that paper received Best Paper Award by TRB Standing Committee on Human Factor and the Infrastructure Design and Operation. So two other funded research on NDS, and Dan and I have been working on. One is innovative safety research based on NDS dataset funded by Auburn University, an internal research project. So the second one is application NDS dataset to improve design guide and associated practice funded by Alabama Department of Transportation. And these two projects investigate some the driver behavior at unsynchronized intersection on multi-lane divided highway, and also studied the driving behavior on deceleration lane on the off ramp. Some of the research results has been published by the Journal of Transportation Research Board. So the key motivation for this phase 2 project is because the state and local agency have applied the various simulation model planning tool to for walk zone the traffic analysis. So for example, causing missing, and both of these models they use the constant headways through entire walk zone. And also they have an input for the driver profile. If you give a driver type and you can customize what is the headway for each type of driver. But there is no data for that input. But this simulation model can calibrate that. And also our planning level tool, Quick Zoom, has been used very outdated field data. That parameter has not been updated. So we are thinking with this new NDS data, we can develop the headway selection table for different type of driver at a different segment of walk zone, and then can provide more accurate calibration for some walk zone simulation tool and the planning tool. So that is a key motivation for this project. So I would like to give you a little bit background on what data we used for phase 1 and phase 2. For phase 1, we actually used a very small sample size, only 76 trips. And also, those trips are very short, only last 21 seconds. And most of these trips just navigate through part of the walk zone, not entire walk zone. We do find 3 different configuration, 2-to-1 lane closure, 2-to-2 shoulder closure, and the 3-to-3 shoulder closure scenario. So the second phase, we like to increase that sample size. We collect 200 trips, and most of these trips are very long, 5 to 7 minutes. And most of them last from the advanced warning area to all the way the end of the walk zone, entire walk zone area. So the configuration include lane closure 2-to-1, lane closure 3-to-2, shoulder closure 2-to-2, and the shoulder closure 3-to-3, and the 4 different walk zone configuration. So the 2 objectives for this project is to develop time gap and headway selection tables based on different driver characteristics, for example, gender, age group, and also their risk perception level for those 4 walk zone configuration. And the second, we like to see develop a speed distribution model to identify where are the key speed change point at the walk zone. So next, I would like to turn it over to Dan. She will present the methodology and the data collection.
Thank you, Dr. Zhou. So the methodology part includes 3 parts. First is the data collection and reduction, and then we'll talk about the headway and gap distribution, and finally we'll talk about the speed analysis. So in the data collection and reduction part, we first had a conference call with Virginia Tech to request proper work zone NDS data. And then they delivered 58-hour sample video clips to identify the work zone start and end milepost. So the trips traversed in the same locations during the same time periods can be exported. And exported time interval covers at most 20 weeks. Typically 10 weeks before and 10 weeks after the identified sample events occurred. But as you know, when work zone activity proceeded, the configuration can change very soon. So for example, although we identified the work zone start and end milepost from the first step, but the work zone configuration might have changed within 2 weeks or even within 2 days. So we reviewed all the videos to ensure that they were categorized into the proper work zone configuration. And the data we received are the time series data, which provide speed, radar data, which provide the time gap, and video clips of the forward roadway as the driver region. And all the time series data and radar data were collected at 0.1 second interval. And we also received the driver risk perceptions and the driver demographics. Next slide, please. Yeah, and this slide shows the example of the data we received. As you can see at the left side, this is the time series report. We have the speed data and the radar data. Here it shows the headway, but it's actually the gaps between the participant vehicle and the front leading vehicle. And we have the video clips of the forward roadway. So, and we also have the time stamps as the orange frame here. So we can link the videos to the time series report, then you know at each 0.1 second what's going on the roadway. So to do the data reduction, this is to eliminate the potential distraction or impact by non-work zone elements. So only trips that occur during the daylight time with a clear region in a good weather condition on the dry pavement were selected. And secondly, to reduce the impact of interchanges near work zones that might potentially influence driver performance, the trips near interchanges were also filtered to exclude the effects of merging or divergent maneuvers on the driver behaviors. So finally, we selected 200 trips driven by 103 unique drivers from 4 work zone configurations, 2 types of lane closure and 2 types of shoulder closure. And it covers nearly 1,100 miles traveled, 19 hours traveled, and over 675,000 data points. So a work zone typically consists of 4 consecutive sections: advanced warning area, transition area, activity area, and termination area. So here are the 2 side description of the lane closure work zones. And it is easy to define these 4 sections, but in the shoulder closure work zones, next slide, please. Yeah, in the shoulder closure work zones, the borders among the transition area and activity area, termination area are not very clear. So in this study, the only 2 areas are defined for the shoulder closure: the advanced warning area and the work zone area. And we also include 500 feet upstream and downstream of work zones to figure out the driver behavior changes before and after the work zone. The drivers, the gap and headway. The gap and headway, as we mentioned, the radar data provides the time gaps, not the headway. So we add a 15 feet vehicle length to the space gap and to convert to the time headway. For the drivers, we categorize the drivers into different genders and age groups. And the risk perception score of a driver is the sum of the scores from the questions in the questionnaire. And the driver risk perception was collected from the questionnaire designed to gauge the participants' perception of dangerous or unsafe driving behaviors or scenarios. So which means higher score indicates a more conservative drivers, and a lower score means a more aggressive driver. And we apply the generalized additive model to estimate the driver headway through the entire work zone. It allows nonlinear function of each variable while maintaining the additivity of the model. We use the R package with the GAM function to develop the model. And in the speed analysis, we use the GAM model and also the trend point detection techniques to explore the speed distribution and speed change over the entire work zone. And for the trend point detection, we also use R package with the change point function to examine the current changes in the mean and variance of each data sequence. And then we're moving to the results section. So we have 2 parts of results. First is the gap and headway distribution. We will talk about the driver characteristics, the gap and headway profile, the gap comparison, and headway estimation. And in the speed analysis, we will talk about speed profile and speed change point at work zones. So in the first, the driver characteristics, for driver risk perception, we can see from the first figure on the left, 60% of drivers in the data set have a risk perception score greater than 160, which indicates that these participants have good risk perception and tend to be cautious and obedient to traffic rules. It was found the risk perception distribution in the female the right side two pictures, in the female and male drivers are distributed very different. So approximate 80% of female drivers' risk perception fall into the interval between 140 to 200, but only 55% of male drivers scored within that interval. And 25% of male drivers' risk perceptions fall into the interval between 200 and 220. So in other words, male drivers were self-reported to have higher risk perceptions than the participant female drivers. And in total, there are 52 female drivers and 50 male drivers, so it's kind of balanced in the gender. And despite two very low risk perception cases, the risk perception of female and male drivers range from 120 to 220. And female drivers obtain higher risk perception scores than the male drivers in the same age group. So, and it's also interesting to find that regardless of gender, the risk perception scores increases when with the increase of driver's age. And this page presents the gap and headway profiles by the driver types. So as an example, we only show the results from the lane closure 221 configuration. So the past studies have stated that the younger drivers are more aggressive and have high risks to involve in the fatal crashes when compared with the other age group, which is actually consistent with lower risk perceptions score from the young drivers. But as we can see here, the younger drivers maintained a longer gap and headway than the middle-aged drivers. And actually from the four work zone configurations in the studies, the middle-aged drivers typically maintain the shortest time gap and headway among all age groups. So here is the cumulative headways from the lane closure 221, and it also shows that the male and female in the middle age, they have the shortest headway. So we did not show the space headway because the space headway is equal to the gap spacing plus 15 feet, which is the vehicle length. So we did not present it here. And we developed 4 gap and headway selection tables for 4 work zone configurations. So here's an example from the lane closure 221. It summarized the details of gap and headway distributions and driver characteristics at their gender, their age group, and risk perceptions before, during, and after the work zone. And it also includes the 95% confidence interval from the gap and headway. So this table would be very helpful to improve the adaptive cruise control spacing policies for automotive industry, because taking driver characteristics into consideration when developing the spacing policies will contribute to the similarity of human drivers' spacing behavior in the adaptive cruise control systems. And that would improve drivers' acceptance and system utilization by introducing driver characteristics. And second, this table would be helpful to improve the work zone capacity models. So because the design time headway parameter CC1 in the WISM is a static value through all work zone consecutive sections. So if headway distribution models built for different driver characteristics can be used instead of a static value in the WISM, a more accurate capacity estimation can be captured. This page shows the gap spacing distribution by different work zone consecutive sections. So also this is an example from lane closure 221. It can be found that vehicle maintain different gap spacings in different work zone sections. For instance, for the lane closure 221, the mean gap spacing from the start section to the end sections are 225, 246, 213, 191, 262, and 242 feet, respectively. So the lower quartile can be treated as the critical gap spacing that most drivers would maintain a gap that is longer than that. And from the box plot, the range of the upper quartile and lower quartile in the main gap spacing have the tendency to decrease as vehicle moving from the start section to the transition area. And the main gap spacing begin to increase after traversing the activity area. This slide presents the best fitted curve of the time headway throughout the entire work zone at lane closure 221. So we can see that the time headway tends to increase when drivers approach the advanced warning area, and it starts to decrease when drivers are in the advanced warning area, and the decreasing trend continues until drivers are at the end of activity area. And the headway quickly increases after drivers enter termination area when drums are removed. So here is the speed profile in the entire work zone at lane closure 221. So the x-axis is the length of the work zone, and y-axis is the speed in mile per hour, and the black dots are the speed data from the NDS time series report, and one trace coming from one traversal. The red lines are the best fitted curves by using the GAM model. And we can see that the speed decrease when approaching the work zone, and the reduced speed limit sign of 55 miles per hour is also presented at the advanced warning area. But drivers only comply with 55 miles per hour speed limit during the transition area and at the beginning of the activity area. And this speed increase when entering into the activity area. And this is the speed change point detection of the lane closure 221. This is used to identify the points where both mean and variance of speeds had significant changes. So the x-axis is the data point index, and y-axis is the speed. So as aforementioned, the speed reduction requirement from the reduced speed limit sign only presented at the advanced warning area, and that's why there is a speed reduction there. The mean speed began to decrease by 8 miles per hour after entering the advanced warning area, and increased back to the initial speed after drivers saw the drum has been removed at the end. So in conclusion and potential applications, the gap and headway selection tables reveal that car following behaviors are highly variable among different drivers. So for the time and space gap distributions from different drivers traversing various work zone areas can be useful to improve adaptive cruise control spacing policies for automotive industry. And further studies are needed to understand drivers' acceptance of current adaptive cruise control gap setting at work zones. And secondly, the headways change through work zone consecutive sections. So separate headway distribution would be useful for different work zone areas when modeling the work zone traffic control using simulation or planning tools. And for the future work, so current NDS database have limited trips and work zone configurations. So if we can collect more NDS data to further validate the gap and headway distribution and selection and speed distribution for different driver types for more work zone configurations would be great. So here are some upcoming webinars that you can register. You can use the registration link in the chat box to register the upcoming webinars. And this is the end of our presentations. And if you have any questions, please enter your question in the chat box and complete the survey by clicking on the link in the chat box. Thank you.
Thank you, Dan. Let me see if we have any questions from chat box. I didn't see any so far. Yeah, please, if you have no question before you leave, please complete the short survey, 30 seconds. Just click that link in the chat box. All right, we got one question. Can you explain what does lane closure 2-to-1 means? Okay, lane closure LC 2-1 means on the freeway, if you have normal is a 2-lane, there's 1 lane closed for the walk zone. So the lane closure from 2-lane to 1 lane.
Dr. Can you go back to the slides that shows the site description? We have 4 configurations and yeah, here we have
this is 2-to-1.
Yeah. We have 2 types of lane closure and 2 types of shoulder closures.
How about shoulder closure 3-to-3?
Yeah.
And this is
The bottom
shoulder closure 3-to-3. You have 3 lane, no lane closure, but just some work on the shoulder. Okay, good. Thank you. All right, so if no other question, I think we can thank you all for coming. So if other question, you can feel free to contact us. I don't have email. I can provide my email address at in the chat box. So that's my contact information. And the final report will be published probably by the end of this year sometimes. Yeah. Thank you.
Thank you.